Hello and welcome back for some more stiffness method solutions. Today we'll be looking at another example of an exam, this time with a truss. So let's see what the question is and let's solve it together. This is the question that we're going to solve today. As you can see, it's a truss with 3 members and 2 pin supports at A and at B. E and A are given to us, and we need to do 3 things in order to solve this exam question. 1, find the full stiffness matrix. 2, find displacements at C. And 3, find internal force members. We'll go through this step by step together so you can see exactly how to solve it. If you are a bit rusty on the theory, go back and have a look at that, but I will give subtle reminders as we go through. Let's start solving. Okay, so this is the truss that we need to solve. Now, before we start solving, I am going to quickly note the degrees of freedom. So since this is a truss, there are 2 degrees of freedom, horizontal and vertical at each node. So at A we've got 1, 2, at B we've got 3, 4, and at C we have 5, 6. So 6 degrees of freedom in total. As we said, the first thing we need to do is find the stiffness matrix for the whole structure. And to do that, I just want to quickly put out a reminder. So each truss in its own local coordinates has a local stiffness matrix of EA over L, 1, minus 1, minus 1, 1. Okay? You can go back and see exactly how we developed that in lecture number 2. There's also a transformation matrix, and that happens when we need to transform the coordinates from a local system to a global system. And we can see here that there are 2 elements, BC and AC, whose local coordinate system does not match the global coordinate system. So we'll definitely need that. And that transformation matrix was CS 0, 0, 0, 0, CS. Again, exactly how to develop that, you can go back to lecture 5 and have a look. To get the stiffness matrix for an element in global coordinates is Ki equals the transformation matrix transposed times the local stiffness matrix times the transformation matrix once again. And if we do that, if we multiply them, we will find that K equals EA over L times C squared CS minus C squared minus CS, CS, S squared minus CS minus S squared minus C squared minus CS, C squared, CS, and finally minus CS minus S squared, CS, and S squared. So this is the stiffness matrix for each element in the global coordinate system after I've found C, which is cosine theta, and S, which is sine theta. So that's the angle at which they're oriented compared to the horizontal. And once again, any recap of the theory, you can go back and have a look. But knowing all of this, we are now going to delve straight into the elements that we have. So we're going to start with element AB, and we can see that AB is this element between degrees of freedom 1, 2, and 3, 4. And so for AB, we have a length of 2 meters, we have an angle of 0 degrees, which means that C, which is cos theta, is 1 in this case, and S, which is sine theta, is 0 in this case. So KAB equals EA over 2, and if I just substitute what we just discussed, C squared, so 1 squared, that gives me 1 here, and then CS, which is 1 times 0, gives me 0 here, and I can continue calculating like that and end up with the following matrix, minus 1, 0, 1, 0, and finally all zeros. Now, since L is 2, I'm just going to divide it by 2, and I'll get that it is EA times 0.5, 0, minus 0.5, 0, and just so on to get my final matrix, just essentially dividing everything by 2. And what I'm going to note here are the degrees, the relevant degrees of freedom. So 1, 2, 3, and 4. And here I've got 1, 2, 3, and 4. And just noting them like that will make it really easy when I come to assemble the full matrix. So that's element AB finished. Okay, let's move on to element AC. So element AC, we can see here, is this vertical element here between degrees of freedom 1, 2, 5, and 6. So if I write that down, and I'm just going to choose a different color for this, element AC has a length of 2 meters. In this case, theta is 90 degrees, which means that C, which is cos theta, is 0, and S, which is sine theta, is 1. And in the same way, I can use that matrix after transformation like before and get the EA over 2 because the length is 2. And here, if I start calculating my matrix, I can see that I've got 0, and then all of the row is zeros, and then here I've got 0, but here I do have 1 because I've got sine squared, 0, minus 1, another row of zeros, and a row of 0, minus 1, 0, 1. So that is just taking now that matrix and dividing everything by 2 just to make it simpler. So I have EA and just dividing everything by the length of 2. And once again, I want to note the degrees of freedom. So if I go back to have a look at element AC, I can see that the first 2 degrees of freedom are 1, 2, and the second degrees of freedom are 5, 6. So let's note that here, 1, 2, 5, and 6. And moving on to our last element, BC. So BC is this diagonal element between 3, 4, 5, 6. So a little bit more complicated, but let's do it. Element BC. Now in this case, L equals 2 square root of 2, and theta equals 135 degrees, because if you recall from the lecture, we measure the degrees from the horizontal. So if this is x, this is theta, I know that here we have 45 degrees, so this is 135 degrees from the horizontal to where this member is. Additionally, C, which is cos 135, works out as minus a square root of 0.5, and S, which is sine 135, works out to be plus a square root of 0.5. And now that we have all that, we can write KBC, so it's EA over 2 square root of 2, because that's the length. And in here, essentially, we have multiplications of minus the square root of 0.5 and plus a square root of 0.5. So everything really is going to be 0.5. So we've got 0.5 here, then minus 0.5, another minus 0.5, 0.5, and I can continue to fill that in. And that's it. We can divide by 2 square root of 2, and that'll give me EA. And now if I divide this 0.5 by 2 square root of 2, everything is going to be either plus or minus 0.177. So plus and then minus. And once again, just adding those degrees of freedom. In this case, it's 3, 4, 5, 6. So here I've got 3, 4, 5, 6, and 3, 4, 5, 6. And that's now it. I have found the stiffness matrices for each element in the global coordinate system. So now that I have each of these elements in the global coordinate system, I need to assemble them together to the full stiffness matrix. Okay. Now I know that this matrix K is going to be multiplied by EA, And we have 6 degrees of freedom. So put them here. And now I'm going to add everything in. I'm going to start off by seeing where everything adds in. So let's just schematically draw that first. Okay, so let's have a look at this. The members for KAB are between degrees of freedom 1, 2, and 3, 4. So 1, 2, 3, 4 here, and then down here to get 1, 2, 3, 4. This is where KAB is going to sit. Then I have KBC, which we just solved here, and we said it was 3, 4, 5, 6. So 3, 4, 5, 6 gives me this location here, and that is KBC. And the very last one that I have, which is this one here, KAC, is 1, 2, 5, and 6. So I have a pocket here, 1, 2, 1, 2, at 5, 6 with rows 1, 2, and then I have a pocket here where the columns are again 1, 2, but the rows are 5, 6, and then obviously 5, 6, 5, 6. So it'll be in these locations. So those all will be KAC. Now that I know what it looks like, it's going to be really easy for me to put everything in. So let's do that. Okay, not forgetting EA and just starting to write everything down. So I'm going to start with members of AB. I find the easiest thing to do is just write out whatever you have in the right locations and then add. So for that I have 0.5, 0, minus 0.5, 0, and I'm just going to continue adding everything in. And that is 1, 2, 3, 4. We'll add here space for 5 and 6, and then the rows 1, 2, 3, 4, 5, 6. Let's now add everything from KBC. So for BC, I start at 3, 3. So here I have plus 0.177, and I'm just continuing to add minus 0.177, and here I had just minus 0.177 and plus 0.177. And I'm just going to continue adding everything from all the stiffness elements for element KBC. And that's all of the members from KBC. And lastly, we'll add KAC. Now here I'm just going to be quite careful of where I put them. Obviously, I've already figured this out. I'm just going to go row, row. Here I add 2 zeros. And I'm also just specifying the zeros just to kind of clarify where everything is coming from. Five, and then the last 4 locations at everything to do with columns and rows 5 and 6. Okay, only one thing here, so it's plus 0.5. And now I can quickly add everything together and get the final stiffness matrix. And that's it, that's the full stiffness matrix. We've solved the first part of the question. I am just going to add the degrees of freedom here because I will need them later. So the next part of the question was to find the horizontal and vertical displacements at C. So that is degrees of freedom 5 and 6. And if we recall, the full equation is K times D, the vector of the displacements, equals the vector of force F. We know K, we've just found that. We know F because F are the external loads, so we know the external loads on the truss. And so what we're looking for really is this here, the displacements. Now we do not have to solve everything. So if we recall, we have our full matrix, So if we write that out with the degrees of freedom, just to note, just to make this easier to understand, I'm not going to write out the full thing. We have EA here that we shouldn't forget. Then we have the displacements. As we said, at each node you can get a horizontal and a vertical displacement. So just writing those down. And that equals the force vector, just putting them in the degrees of freedom. So you can see force 1 to 6. But we already know what these are. If we go back to our question, we can see that at node C, we only had a horizontal force of 60 kilonewtons. So that is 60 kilonewtons in the positive direction of degree of freedom 5. Everything else is going to be 0. So now we need to note here that degrees of freedom 1, 2, 3, and 4 are restrained. That means they can't move. There will be no displacements in those nodes because they are all pinned. And because of that, we can get rid of the rows that are definitely going to give us 0. So 1, 2, 3, and 4. And likewise, we can also get rid of the relevant columns. And that leaves us with this little bit of the stiffness matrix here, KFF, the 3 degrees of freedom, which is this bit here, DF, and the external loads on those 3 degrees of freedom, FF. And that's all we need to solve to get the displacements, because as we said, all the other displacements are 0. So let's now write that with the numbers that we already found. So you have EA, and then we just need this little bit of the matrix just for degrees of freedom 5 and 6, and that is 0.177 minus 0.177 minus 0.177 and 0.677. We need to multiply that by U3 and V3, and we already know that the force is 60 and 0. And that really gives us 2 simultaneous equations. Let's write them down. So equation 1, coming from the first row, 0.177 times U3 minus 0.177 times V3, all that multiplied by EA equals 60. And equation 2 from row 2, minus 0.177 U3 plus 0.677 V3, all that times EA equals 0. We can just divide everything by EA, so this becomes 60 divided by EA, and obviously here it's 0 divided by EA, so that remains 0. I'm going to add equation 1 plus equation 2, because I can see that I've got 0.177U3 and minus 0.177U3, so they will cancel each other out. And if I do that, I get 0.5V3 equals 60 divided by EA. So V3 is 60 divided by 0.5, 120 over EA. Now, E is 210,000 newtons divided by millimeter square. And note that until now, I've been using kilonewtons, that 60 is in kilonewtons, and I've been using meters because I've put all my length as 2 meters and 2 square root of 2 meters. So I'm just going to convert these into those units. So that gives me 210 times 10 to the power of 6 kilonewtons divided by meter square, or kilopascals. And A, which is 100 millimeter square, becomes 1 times 10 to the minus 4 meter square. And due to that, V3 is 120 divided by 210 times 10 to the power of 6 times 1 times 10 to the power of minus 4. And that gives me 5.714 times 10 to the minus 3 meters. That's the displacement. Or if I want to write it back in millimeters, just multiply by 1,000, so 5.714 millimeters. Substituting back into equation 2 gives me that U3 equals 0.677 V3 divided by 0.177, and that works out as 21.86 millimeters. And that's it. We have now found the displacements as well. And the last part of the question was to find the axial forces in AC and BC. If we go back to lecture 8, we'll see that the forces in their local coordinates, which is what we need to find the axial forces, equals the stiffness matrix in local coordinates times the transformation times the displacements in the global coordinates. As we said, in local coordinates, the stiffness matrix is very simple. This looks like this. And we also said that the transformation matrix is. So knowing those two, we can just go one step back and find the axial forces in local coordinates. So let's start off with element AC. So as a reminder, L was 2 meters, C was 0, S was 1, EA, just going to write that here, is 21,000 kilonewton meter square, just matching my units. And the only other thing I need to get out of here is what is the displacement vector in the global coordinates. Now, AC was between nodes 1 and 3, so it was U1, V1, U3, V3, and we know that U1, V1 came out as 0 because they were restrained, right? At node 1, we had a pin support, so we just need to take these out of the solution that we just found. So U3 worked out as 21.86 times 10 to the minus 3. I just want to work in meters now. And V3 was 5.714 times 10 to the minus 3, also in meters. So that was the only thing I had to add here. Now I'm just stressing here that you can see how important the units are in all of this. So let's solve this. We have FAC in local coordinates equals EA. I've already popped in the length of 2, so I've got here 0.5, minus 0.5, and minus 0.5, and 0.5. Then I have the transformation matrix, which works out as 0, 1, 0, 0, 0, 0, 0, and 1. And the displacement vector, which had 0, 0, and then 21.86, 10 to the minus 3, and 5.714, 10 to the minus 3. And that's what I need to solve in order to find the forces. I'm going to do it step by step, but obviously you can do it in any quicker methods that you know. So EA 21,000, this just for a second remains as is. And then I'm just going to multiply the transformation matrix times the displacement vector. So you can see in row 1, I've just got 0 times 0, 1 times 0, 0 times 21.86, 10 to the minus 3, and 0.5.714, 10 to the minus 3. So you can see here that I get 0. And for the second one, we can see that just the fourth member in that row is 1, and the fourth member in that column is 5.714, 10 to the minus 3. So that's really all I have here. And now I need to multiply the stiffness matrix by that vector. So just leaving that 21,000. And here I've got in the first row, just the second members give me something. So 0.5 times 5.714, 10 to the minus 3. And in the second row, again, it's just the plus 0.5 times 5.714, 10 to the minus 3. And if I multiply everything, I get minus 60 and plus 60 kilonewtons in both cases. And if you recall from the lecture, we go by the last member of the vector. So this is 60 kilonewtons in tension. And we'll now do exactly the same for member BC. And in this case, the length was 2 square root of 2. C was minus a square root of 0.5, and S was a square root of 0.5. The only other thing I need to get is the displacement vector. Now, BC is between degrees of freedom 3, 4, 5, 6. So I need to take out U2, V2, U3, V3. And so once again, I've got 0, 0, and then here I've got 21.86, 10 to the minus 3, and 5.714, times 10 to the minus 3, and that's the displacement vector. So once again, putting everything together so that I get back into the local coordinates, EA, and here I get 0.35, because essentially it's 1 divided by 2 square root of 2, and minus 0.35 and 0.35. That's the stiffness matrix in local coordinates. Then I've got that transformation vector, so minus the square root of 0.5 plus the square root of 0.5, 0, 0, 0, 0, and then once again minus 0.5 plus 0.5. And finally, that displacement vector that I just found. And just like before, I'm just going to open these up and solve it. Now this part here works out as minus 0.0114, and so here I get 21,000 times minus 0.35 times minus 0.0114, and here I get similar, just with plus 0.35, and that gives me 83.9 kilonewtons and minus 83.9 kilonewtons. And again, we go by the last one. So here we have for this member 83.9 kilonewtons in compression. And that is thus also solved the forces, and that brings us to the end of the question. So we've done, as you can see, quite a lot of work. We started off by finding the stiffness matrix for each element in global coordinates. We then added them together to get the full stiffness matrix for the whole system. We then solved that together with the external forces that we knew to find the displacements, the free displacements. And then we used those displacements along with the transformation and the local stiffness matrix to get the forces in the local coordinates. And that brings us to the end of the question. Thank you for joining me. I hope you found this session useful. In this session, we covered another exam-style question, only this time it was a truss. As we saw, the truss in its local coordinate system is really simple, but when we move the stiffness matrix into the global system and also locate where every little bit of it goes, it can be a bit more complicated. So take your time and practice, and it'll become easy.